Hello everyone, let me just share my screen. So let's start. What is a microcontroller? So a microcontroller is basically a small computer on a single metal oxide semiconductor IC chip. A microcontroller contains one or more CPUs or processor cores, along with memory and programmable input and output peripherals. So if you've ever programmed an Arduino, the Atmega 3328 chip is the microcontroller, and the Arduino can be considered the breakout board for this microcontroller. And peripherals are just devices that aid the microprocessor to accomplish a given job. In other words, they serve as accessories to the microprocessor. Some examples of peripherals include GPIO controllers, which are responsible for the input and output operations for the pins. We have timers. We have serial communication controllers for UART, SPI, I2C, and Ethernet. There's also CAN. We have interrupt controllers, and we have analog to digital converters. These are just some of the examples of the peripherals. So mastering a microcontroller is mastering its peripherals. If you can use all the peripherals of a certain microcontroller, then you can accomplish whatever task you want to do with the microcontroller. So for this workshop, we'll be using the STM32F103C6 microcontroller. And STM32 is a family of 32-bit microcontrollers by STM Microelectronics. And they are grouped based on the ARM processor core they're using. For our microcontroller, we'll be using the Cortex M3. So these are some of the peripherals for the STM32F103C6. We have 6 timers, 1 I2C interface, 2 UART interfaces, 1 SPI interface, we have CAN interface, and 2 analog to digital converters. There are more peripherals, but these are just some examples. So let's start with the Gpio interface. The Gpio, as I mentioned earlier, is used to set pins as either output or input, as well as control the switching speed, pull up or pull down properties. Usually when dealing with GPIOs, we'll see the active low or active high configurations. For active low, the interface is receiving a high value or 5 volts until the switch is closed. Then it's shorted to the ground, meaning that when it's active, the interface receives a low value. For the active high, it's connected to the ground, and then when the switch is closed, the 5 volt is connected to the interface. So let's start making the project. I hope you've already downloaded and installed both Proteus and STM32. Let's start by creating a new project and go to new project. Choose where you want to save the project. Then let's name it Workshop Day 1, for example. We'll just choose default for the design templates. And we do not need to create a PCB layout. We're going to do a firmware project, so we'll select the firmware project. For the family, we'll need to choose Cortex M3. And then for the controller, we'll scroll down to STM32F1036. Then press next. And that's it. It should start creating the project. It will also create this source code tab, which we don't need since we'll be using the STM32Cube IDE. So just close this one. And this is our microcontroller. So let's start by adding one LED to test. You can go to this component mode and then press on E. Let me share the name of the controller.
Anas, excuse me, speaker or participant want you to speak slowly, so like speak a little bit slowly.
Okay. I'll send the name of the microcontroller to the chat. So once you have your project set up, you need to go to components and then click on the P, or you can just click on P on your keyboard and it will open up the component menu. Let's
Anas,
first add.
excuse me. Can you repeat these steps again so we can follow with you
And create a new
from the
project.
beginning? Yeah, sorry for that.
And just go to new project. Choose where you want to save the project. Let me create a new folder. Name your project. Choose whatever name you like. And just press next. For this, design templates. Just choose default, don't change. Then press next. We do not need to create a PCB layout, so just choose do not create a PCB layout. And next, we'll choose create a firmware project. So the second one. For the family, we're gonna use the Cortex M3. So just choose Cortex M3. And then for the controller, scroll down to STM32F103C6. I've already posted the name inside the chat. And then,
please, can you repeat it from the beginning? Sorry to interrupt you.
Okay, I'll just go back. This is the first project name. Just choose your name and then choose the path. Then just click next. Choose default. Then press next. You need to choose do not create a PCB layout. It's already chosen, so don't press anything. And then for this, we need to create a firmware project. And then choose Cortex M3. And for the controller, choose the STM32F103C6. Is it okay? Then just press next and then finish. We don't need this source code tab, so you can just close. and you'll be left with this one. Once you open this page, you can press P on your keyboard or go to components and then press on this P. Once this is open, you can just type in LED. I have a choice of multiple LEDs, but this one is animated, so choose one of the animated LED models. You can choose the color also, just choose green. And press on OK. Then
Okay, Anas, is it a problem if the controller is not configured in my software?
the software should already come with the controller inside the library. But if you cannot access the library, maybe try running as an administrator. Should solve the problem.
All right. And a second question, for the schematic LED, how did you get it? Can you repeat the previous step?
Yep. You can just press on P on your keyboard, or you can just go to this component mode and then press on this P. Once this screen opens, you can type in LED, then scroll down. This is the default LED, but we'll just go to the animated LED model. You can choose whatever color you like. There's blue, green, there's orange, pink, and so on. I'll just choose green. Then press OK. Then just press once, and you will have to add it. You can press on the plus button to rotate it, or the minus to rotate it the other way. And let's place it somewhere. Let's see. Just pen P1. Let's connect to the pen. And then let's add one resistor. So the same again, just go to the components and then P, or just press P on your keyboard and then search for resistor. Press OK and add the resistor. Press the plus button to rotate. Then just take it. Connect them. And then finally, need to add ground. So we just go to this terminals mode, and then click on ground. And then add it to your design. Connect the resistor to the ground. And then we have our first LED. Is everything okay so far? If yes, we'll move on to the STM32 project.
Excuse me, could you tell me how did you rotate the LEDs?
Using the plus button on your keyboard. Just press plus or minus.
Okay, thank you.
To connect the LED, just press on one of the terminals and then press on the other one. So if I delete this one, just press here, then you have this wire, and then press on the other one. Okay, then let's move on to the STM32 Cube IDE project. Should have a screen similar to this one. Just go to File, and then New, and choose STM32 project. So again, File, New, STM32 project. It should load the target selector to choose our processor. Just tick off the STM32F1 family. Then you can expand this one to see clear. Scroll down until you find the 103C6, which is the one we're using, which is this one. And then press next. Enter the name for your project. Say workshop for day 1. Then just press finish. So you'll directly see the screen once the project is created. Is everyone following, or do you need some time?
Can you repeat again from new project until this step?
Yep, can. Just click on File, New, and then STM32 project. Then the target selector will load up. You can press on the STM32F1 to just choose this family, which is the F1 family. Maybe expand this one to see clearer. And then scroll down until you find 103C6. Just make sure you're inside the MCU selector, not the board selector or the example selector or any other. Make sure you're inside the MCU selector. Once the microcontroller is selected, just press on next. It will ask you to enter the project name, and then you'll just press finish. So should we continue, or do you need more time? At this point, you should have one Proteus project with one LED, and then the STM32 Cube ID project showing the processor. Okay. So one thing we need to configure first is the clock. So press on the second tab, which is the clock configuration, and you'll see this screen. So let me zoom in. We're concerned with this part for now, which is this flow starting from HSI. So HSI is the internal oscillator for the microcontroller, and it's currently set to 8. And then you have this multiplexer. It just chooses between the internal oscillator, external external oscillator, or the DLL clock. For now, let's just be concerned with the internal oscillator. Just go with the flow. This is 8 megahertz, the same. And then you have a prescaler of 1. We can change the prescaler, but generally we need the most speed. And then move to the APP1 prescaler, which is connected to both the peripheral clocks and timer clocks for APP1. And then you also have the APP2. Generally, we need our microcontroller to be running at the fastest speed. So we need to choose the PLL clock, this one, since it has a multiplier option. So what this does is just multiplies the internal oscillator. So the internal oscillator passes through this divider, so it gets divided by 2, so it's now 4. And then we get to multiply it by a certain number. Let's choose the most, which is 16. And then you'll notice that now we're outputting 64. But this is already over the max, which is 36. So we can divide this by 2, achieve 32. So this is the setup we'll be using. So again, instead of choosing the internal oscillator directly, which is HSI here, we'll choose the PLL clock. For the multiplier, we're choosing 16, which is the most. And then for the APP1 prescaler, we're going to divide by 2. Is everyone okay on this? If we had an external oscillator, we could directly use the external oscillator or do the same. Feed the external oscillator into the PLL and then multiply the clock. But we'll just use the internal oscillator for now and then multiply it using the PLL clock. This is our clock configuration. Then let's configure our LED that we just connected. We connected the LED into pin P1. So what we can do is go to P1 here and then choose GPIO output. And the pin is already configured as an output. If you go to System Core and then GPIO, you can see the currently activated pins, which is this pin P1. It's flashing. And we see some configuration options. So the GPIO output level is the output level at the start, so we'll just initially be low. For the GPIO mode, we have either push-pull or open drain. Push-pull means that it's either high or low. So if the pin is not high, it's going to be low. It gets pushed to a certain state. For open drain, it can be floating, which is neither high or low. So we'll just choose push-pull. There's also pull-up and pull-down resistors, or you can choose not to. Usually, if you need your state to be, for example, pulled up, so pull-up means that it's connected internally to 5 volt through a resistor. And pull-down means that it's connected to ground internally through a resistor, meaning that the value will be high, for example, if it's pulled up. Can you please mute your mic? So it will be, if it's pull up, then it will be 5 volt by default, even if it's not connected to anything, until something else outside grounds it. So for now, I'll just choose no pull up or no pull down. And then we have the maximum output speed. So we have either low, medium, or high. For now, we'll not be switching. This is the switching speed. So let's say we're switching at a speed of 2 megahertz, switching between high and low. So, okay, that's low. We have medium or high. To know the exact speed, we can check out the datasheet. So this is the datasheet for the STM32F0136. And then this is the reference manual. Both we're going to be using. The reference manual is contains more information on exactly the registers and how to program. But the datasheet just contains the specifics for this model. I'll send both to the group. So you can download and check out the sheet. But for now, let's check the GPIO in the reference manual. So for the reference manual, it includes for the entire family, so the entire F1 family. It's more general, but you can go check the general purpose alternate function IOs here. And if we scroll down, we can find that this one is low, which is 2 megahertz. The medium is 10 megahertz, and the high is 50 megahertz. So any information that will not be included inside CubeIDE itself can be found in the reference manual. Okay, so if you go back, this is now configured, and we can start generating our code. But before we do that, I want to change something. If you go to Project Manager, and then go to Code Generator, I recommend checking this, which generates a different .c and .h file for each peripheral. Makes it easier to manage your project. So we'll check this one. So again, this is the third tab, which is the Project Manager. Go to Code Generator, and then check this one. Generate peripheral initializations as pairs of .c and .h files per peripheral. Is everything okay so far? If everything is okay, we can just press Ctrl S to save, and we'll be prompted to generate code. Press yes, and it'll start generating the code. Since we already chose the bin that we need, we will just initialize the bin. So let's analyze the project. If you go to the project here, which is Workshop Day 1, we have core and we have the drivers. The drivers include the whole drivers, which we'll be discussing for a while. And then the core contains the source file and include files that we'll be using. So this is the main, which is this main.c. And then it also generated the gpio.c. We'll check it out later. For now, let's check the main code. You can see this is the system clock config. We found slightly down. So this is the clock options that we choose just now. We're using the internal oscillator, HSI. It's on. Calibration is the default calibration. We didn't change anything. And then we're using the PLL clock. So PLL is on. The HSI is divided by 2, as you can see. Go back to clock configuration. The HSI is passing 2 divided by 2. So this is this one. Then we're multiplying by 16. These are the options that we just now configured. And these are the options for the second part, which is this part, the APP2 or APP1 clocks. You can see that for APP1, it's being divided by 2, which we just now configured. And this is being divided by 1, the APP2 clock. You can notice the structs are being used to hold the data. The struct is just like a class, a holder for multiple variables so that they can be accessed inside the namespace of this struct. So this is one struct and this is the other struct. And they are being passed to the whole library as arguments to the function in order to configure the clock. So this is the system clock config. There's also the whole initialize, which is called at the beginning of the program. Initializes the whole library, configures the registers and everything. This must be called. And then we have the GPIO initialization, which we just now configured. But this is not inside this file, it's inside the other file, the gpio.c. So if you ever see a function or anything that you want to go to the definition of the function, you can press on F3. So on the keyboard, press on F3, and you'll go to the definition of the function. So this is the initialization for pin P1. This is a struct that holds the initialization, and this is the clock enabled for Gpio P. So usually, for all peripherals, you need to enable their clocks before dealing with the peripheral. For the GPIO, we have a clock for each of the ports, port A and port P, for this microcontroller. And then later on, any other peripheral will also need to enable its clock. Then this sets the LED as low. So this is GPIO pin reset. We'll be using this function to set as high later. It's just hold GPIO right pin and then the pin port, pin number, and then whether it's high or low. This is an enum. This code is auto-generated once you press Ctrl S here. Once you save this, it will prompt you to generate the code. This is all generated from this code. So inside, this is the initialization struct, which is this one. We're just setting the pin to pin 1, the mode to output, and then PP stands for push-pull. And then the pull mode is no pull. There is no pull up or pull down. And the speed is low. Once we've loaded all the arguments inside this struct, we can call the HAL Gpio initialization function, pass in the port, which is port P, and then pass the struct by reference. This means this address mark means that the function requires a pointer. You just hover over the function for a while. You can see the function definition. This requires a pointer to the GPIO struct, initialization struct. So we're passing with an address. If you want to know what's inside, you can just hover over the struct and it will show you the variables inside. Or you can press on F3 also, and it will show you the struct definition. This is all auto-generated. I'm just explaining the generated code. So we have HAL initialized, we have the clock configured, and the GPIO pin P1 is initialized. So we can start writing the main code. But before we write the main code, I want to show you what's inside the other files also. So this is the HAL MSB file. It contains the MSB initializations for different peripherals and for the main program. But since we divided them into other code parts, which is gpio.c, then this will only include this function, which is just the initialization for the main whole program. And then we have this it.c, which stands for the interrupt. This contains all the interrupts. These interrupts we're not going to use for now. These are just system interrupts, but we're going to discuss the systic handler. So systic is a timer that runs every 1 millisecond and has this function. You can add other functions, but by default it has the HAL increase tick, which is used by the HAL library. We're going to use HAL delay later. So HAL delay operates using this interrupt, which is the systic handler. These are the main files you should know about.
Hello, Anas.
Yep.
Can you enlarge the screen so you can see the code clearly? Is possible?
Can try to zoom in. Is this better?
Yes, better. Yes.
So these were the main files. There's also the inside the drivers. This is the whole driver file and has the includes and the source. So all the structs and the initialization functions and the write functions and so on will be inside this driver file. So if you check out the Gpio driver, you can see the list of functions. You have Gpio initialize, deinitialize, read bin, write bin, toggle bin, and so on. These functions deal with the registers themselves of the STM. And the idea behind the whole library or the whole driver is that you don't have to deal with the registers. You just need to call their functions. And then inside the functions, they're setting the registers to a certain value. So that's it for the driver. We'll be going back to the driver files when we need to check something out, but otherwise we'll just be inside the main.c. So once again, this is the main.c. So let's start writing our main code. Be sure to write your main code inside the user. You see user code begin, and then user code end. So the stuff you write inside these will not be deleted if you generate the code again. But if you write maybe somewhere here, which is outside the end and before the begin of the other part, then your code will be removed when you auto-generate again. So inside while one, let's set the pin whole Gpio, and then press Control and space to show the recommendations. Press Control and space. These are the list of functions that you can call. Let's start with whole Gpio. So let's write pin, whole Gpio write pin. We'll just type in Gpio P. Then for the pin, we're going to use Gpio pin 1. And if you're not sure what you should write in any of the function arguments, you can press F3. And then they discuss in detail what should be write in each parameter. So for example, the first one should be Gpio X, where X can be A to G, depending on the device. The second one is the Gpio pin, which can be Gpio pin underscore X. X can be from 0 to 15. And for the last one, it can be either Gpio pin reset or Gpio pin set, where set means set it to high and reset is reset to low. So if we go back, we can set this to Gpio or pin underscore set. And this is an enum, meaning that these stand for a certain number. If we press F3, you can see that this enum is just reset and set, where reset equals 0 and set equals 1. Since this is an enum, each one is incremented by 1. So if you go back to main, you can actually replace this by 1 if you wanted to, or anything equivalent to 1, and it will still work. So this is our first function, our first line. Then we want to delay for a bit. Then let's type whole underscore, and then press Control space. You can type in delay, and then send. This delay is in milliseconds, since SysTick operates on millisecond intervals. So let's say 200 milliseconds. Then let's write it back to reset. Just change this to reset, to set it to low. Then delay 200 again. So what we're doing here is just set it, then wait 200 milliseconds, and then reset, wait 200 milliseconds, and repeat. So it should blink every 200 milliseconds. One important thing we should do before building this project is we go to project, and then go down to properties. Here we'll go to C/C++ build and settings. Then we're going to choose the MCU post build outputs. and we need to tick this convert to hex file on. We'll use this hex file in our Proteus simulation, so I need to check this. So again, I repeat, go to project, and then scroll down to properties. Go to C/C++ build, and then go to settings, and then go to MCU post build outputs, and check the convert to Intel hex file. Is this okay? Any questions before we move on?
Okay, guys. Anas, can we take 10 minutes break for now?
Yeah, can.
Yeah, okay. We're going to take a 10 minutes break and then we will continue the project. Okay, guys, welcome back. So can we continue now? All right, so Anas, you can complete.
Nice. Hello. We'll just do a quick revision of what we've done so far. So at the beginning, we just created a project for Proteus by going to File, New Project, and then we just chose where to save our project and the name of the project. Press Next, went to Default, then Next. We did not create a PCB layout, then Next. We chose to create a firmware project, chose Cortex M3, and STM32F103C6. Okay. Once we were inside the project, we went to the components, and then we pressed on this P. We added an LED. Is this green LED? Connected it to P1 by pressing on the terminal, then connecting to the other one. Did the same for the resistor. We went to components, P, added the resistor, and then we went to this terminals, selected the ground, and then added the ground, connected this, connected all of them to P1. This was for Proteus. Anyone still stuck in Proteus?
I know, Anas, for the terminals here, I can't extract the ground and insert it to the board. So what are you doing exactly? You are
This one?
picking the ground and then, yes?
Yeah, I just press on the ground and then add it. And then
Double click, right?
yeah, Just click once, will app, and then press again to place.
All right, thanks.
Then just connect. Any other question regarding Proteus?
I guess I have a question about how did you get the ground, the schematic ground?
From the terminals here. This one, terminals mode. Then press on it, and then you will see the list of terminals to the left, and then press on ground. Then go
Okay,
anywhere,
thank you.
press once, and then connect.
Thank you.
Come. Any other question before we revise the STM32 Cube IDE? Then we'll move on to the STM32 Cube IDE. We created a project, started with File, New, STM32 project. We made sure that we are inside the MCU selector. Inside the series, we chose STM32F1. We expanded this a bit. And then we went down and selected STM32F10103C6, which is this one. Is anyone stuck anywhere before this point? Once this is selected, just press next, enter the project name, then press finish. Once this is done, you'll be prompted with this screen. We first click on clock configuration, which is the second tab. We have this screen. We selected the PLL clock, which is the third one. And then here we multiply by 16. And for this APP1 prescaler, we divide it by 2. Is anyone still stuck at this part? If no, then we'll just continue. We went to pinout and configuration, and then we pressed on P1. We selected the output, so P1, output. Then, for this dashboard, we selected GPIO, then clicked on P1. We didn't change any of these. I just explained that output level is low. The GPIO mode is either push-pull or open drain. Push-pull means that it must be either one of the two states, either high or low. Open drain means that it can be floating. For the GPIO pull-up and pull-down, we chose no pull-up and no pull-down. You can choose to pull up or pull down, means that if pulled up, it will be connected internally to 5 volt. The pin will be high by default. And if pulled down, then will be low by default. Then the maximum output speed, we choose low. We also learned that inside the reference manual, low is 2 megahertz, medium is 10 megahertz, and 50 megahertz is high. once we've configured the GPIO, we just pressed Control S. We were prompted to generate the code, and we pressed yes. So far, is everyone able to follow?
Again, how to generate the code? Again,
You
please.
press on Control and S. Press Control and S, or just File Save. There's one more thing inside the project manager. There's this project manager. And then, if you're on project, you select code generator. And then, inside code generator, you check this one, generate preferred initialization. You can as well also ignore this step, or just not have the gpio.c file. They'll all be inside the main.c file. So anyone stuck at this point, at the generation point? If no, then we'll just continue. Once the code was generated, just briefly explain the importance of hard initialize, that the configurations we just now configured for the clock is inside the system clock config function, and the initialization for the GPIO is inside the MX GPIO initialize function. Then, inside the while one, we wrote a simple code to make the LED blink, which is just set and then delay, reset, and then delay. Is anyone stuck at this point, at the code point, or is unable to write the code? These are the only functions we added. These 4 functions, the only thing we added so far. Oh, the rest of the code is entirely generated.
Can you copy this code from while until the end
Yep.
into the shell? Yeah.
Okay. Then we went to project, and then we chose properties, then project, and then properties. Inside this menu, this might be closed, or maybe you're seeing this now, resource. We just click on C/C++ build to expand. And then inside settings, go to MCU post build outputs, and then convert to hex file. Enable this one. We need to generate the hex file. Is anyone not able to do this step? Now someone is asking, why shouldn't we use toggle directly? You can use toggle. I'm just showing the write pen function. We'll use toggle later for the timer. Is anyone not able to follow until now? Just the generation of the hex file. If not, then Just apply and close. And that's it. Now we can press on this build hammer, or you can press on Control and B in order to build the project. You can see that console is building, and then see build finished, 0 errors, 0 warnings, and you can see that the hex file has been generated. Is everyone able to build their projects? Any troubles? This is the build option, which is the hammer. You can hover over it and then just build debug for project workshop day 1. Or you can press on Control and B. Nice. Once it's built, we can go back to Proteus. And we can double click on this. Go to Program File. This one, this option. Again, you just double click on the controller. And then for Program File, we're going to choose the hex file that we just now generated. So we're going to press, we'll go to wherever your Cube IDE workspace is. Mine is here. Go to the Workshop Day 1 project. We're just going to the project you created for the STM32 Cube IDE. If you don't know where your project is, you can right-click, go to Properties, and then Resource, the first one, and you have the location here. You can press this one to show you the location. So just go to wherever you saved your STM32 Cube IDE project. Go to Debug, and then choose the hex file. And just open. Press OK, then done. So is everyone able to choose their hex file? If yes, then we'll just continue. Okay. Any questions?
Should we go to hex files inside debug folder?
Yeah, inside debug, choose the hex file.
Hello, can you show us the properties configuration so that we can generate hex files in the STM32 IDE?
Oh yes, can. These are the properties, project, then properties. Then inside the C/C++ build, we're going to expand, then press settings. And then out of these, we choose the third one, which is the MCU post build outputs. And then enable this one, the second one, convert to Intel hex file.
Okay, thank you.
Any other questions regarding the hex file? If no, then we'll just continue. So now we've loaded the program that we wrote inside the STM32 Cube IDE inside this microcontroller, and we're ready to simulate. So to to simulate, we just press on this run the simulation down, this play button, bottom left, and it should start simulating. You'll see the LED blinks on and off. But keep in mind that this is not the real time. You can see the animation time at the bottom left. So it's blinking every 200 milliseconds. So when it reaches 1.4, it should turn off and so on.
I have a question. How to delete the wire if I shoot the wrong pin?
Oh, you can first choose the mouse button, this one. You'll be able to select, and then just select the wire, drag to select, and then press delete on the keyboard. Just choose and then press delete.
I'm sorry, can you repeat? How did you connect the IDE to the process? Because actually, I have a problem in the file name.
The file name,
Yeah.
you just double click on the microcontroller, and then you navigate to your project file. Let's say this is my project file. Go into debug, and then choose the hex file.
Okay.
And then okay, that's it. So is everyone able to simulate? Should be blinking. Nice. If anyone has any problem, should ask, because this is what we'll build the rest of the workshop on. So you need to have a working simulation in order to continue.
Can you tell how to simulate again?
You just press the play button, the bottom left. You can also go to debug and then run simulation, or press F12. Or you can just press this one. Okay, is everyone okay? Should we continue? So next we'll be just adding 2 push buttons. I'll take input. We will do one active high push button and one active low push button. We'll follow this one. I'll also send to the group an image of what it looks like. So we'll be building the same circuit for routines. We'll do one, one active high and one active low button. So let's start by going into the components. We'll add the same resistor we used. Maybe just rotate it to be vertical. And then we need to add the push button. So we'll press P or press P and search for push. Should be the first one. This is the button. And then we'll just add it. So this one might be the active high push button. So we have the push button and the resistor. We just need to add the ground and the 5 volt. We'll go to the terminals. This is the ground, the same ground that we added last time. Then for the 5 volt, we'll use the power link. So this is the 5 volt. We'll just connect all of them. And then we can just take this and connect it wherever we want. But I prefer to add an output label. So also inside terminals, output. And just connect it to here. And then add an input label to the IC where I want to connect. So this is the input that's connected to 11, for example. So as long as we name them the same thing, they'll be connected. So let's name this push button 1, for example, BP1. 1. Now this is connected to then A11. This is an active high push button, meaning that it will be grounded until the switch is closed, so the 5 volt will flow. Then let's do an active low push button. It will be the same, just reverse the positions for the resistor and the push button. So let's copy all of this. Right click, copy, and then paste. Then let's add them in the other order. We can go to the components and then add the components we previously added without going through the B menu. This is going to be here. And then the button is going to be here. So this is connected to the 5 volt until the button is pressed, then it's shorted to the ground. Let's change this name to button 2. Then let's add an input to A12. So now we have push button 1 and 2 connected to A11 and A12, and one LED connected to P1. So is anyone not able to do the push button circuit? Any questions regarding the circuit, or should I move on to the code part? Okay, let's move on. So we're still in this project in Cube IDE. We'll go back to our IOC file. If you already closed this, you can find inside the project on the left, and then the last one should be the last one. So we'll just press this one again. This time we want to choose A11 and A12. So I'll click on A11, and then this time it's an input. Then A12 is also an input. So you can see they are both added, A11 and A12. Will also not change anything, just input mode, no pull up and no pull down. The other settings are only relevant if it's an output pin. So we just have these two settings. And that's it. You can press on Control S to generate the code. The code will be exactly the same, except for the GPIO initialization, which should now contain all three. So now we have this one, 11 and 12 is A, and we have B is 1, pin 1. These are configured as output, push-pull, no pull-up or pull-down resistor, and the frequency is low. And for this one, it's just input and then no pull. The clock for A was also added, since it's a different clock than B. And these are the only changes for the auto-generator code inside the initialization function. Inside main, we can start writing our logic. So let's delete this. Let's start with an if condition. So let's say if we read from push button 1, so we're just gonna use hall underscore Gpio and this control and space to show the recommendations. And then we'll choose the read bin, hall Gpio read bin. And then we're going to read Gpio A. Then the bin is going to be bin 11, for example, which is the active high bin push button. So let's set the LED to be on, for example. So just hold underscore Gpio. Also again, control and space. And then write bin. We're going to use Gpio E. The bin is bin 1. And we want to set it. So Gpio underscore bin underscore set. Or you can just say set, since it's the same, also equals 1. Or you can just write 1. All of these should work. Let's just set. So if we press the first push button, the LED is on. Then if we press the second one, let's add another if condition, all Gpio again, control and space. And let's read then going for Gpio A and then bin 12. This time we're going to add a not, because this is an active low button. So when you press, it becomes 0. So not 0 becomes 1. So the condition is true. Otherwise, when it's 5 volt, it's high. So not 1 will be 0. So it will not trigger the if condition. So because this is an active low button, we need to add this not. Then we'll just do the same, but reset. So any questions so far? This is the code we're going to use to set or reset the bin using the push buttons. It's just an if condition and then set and reset.
Can you return to the pin and pin in and pin out configuration? So I didn't follow with you the inputs there.
This one, A11 and A12. Just click and then choose GPIO input. Both of them are
Right.
inputs. Okay. So should we move on? Let's see. Let's first build. Press Control and P. Build. Control and P. Should also generate the hex file. Since the hex file is already chosen for Proteus, we just can directly simulate. Just press on the simulation. Now it's running. So you can see that the active low push button by default, the red means there's power there of 5 volt. So it's already delivering 5 volts by default. And then the active high is delivering 0 by default. And then when we press, it will deliver a high. Then the LED turns on. And then this is high. And then when we press, it goes to low. And then the LED turns off. So any problems so far with the simulation? Just on and turn off. So at this point, does everyone have his 2 push buttons ready with 1 LED and the simulation works? Because we're going to continue using these push buttons and the same LED for the next peripherals also. So
Is it okay if I use block copy for the first one and copy it as a second one?
yeah, it doesn't matter if it's an active low or active high, just 2 push buttons. Okay, so if everything is okay, this is the end of the first session, which is the GPIO session. For the next session, we'll be talking about timers. So would you like to have like a Q&A session, or is everything okay? We can just continue to the timers.
If there's no questions, we can take a 10 minutes break again.
Okay.
So anyone has a question to ask before we go for the break? All right, we can take a 10 minutes break. So we will continue on 6:45 for session number 3 about timers. We are going to be back after 10 minutes. Thank you.
Yep. Hello. So let's revise just briefly. So for this screen, we selected P1 as an output because we will need to send the voltage to the LED, which is an output compared to the microcontroller itself. And for the push buttons, we've selected them as inputs. As they provide the voltage, we want to read their value. So we've selected them as inputs to the microcontroller itself. And that's it. For the if conditions inside, we've selected to read pin A11, since it's the pin connected to push button 1. So we need to find the value of when we press the button, the value changes. So we need to detect this change. So this means when a change happens, and this change is 1 for this active high button. So normally it would be low, so this condition would keep getting refused, so it will be false because it's 0, it's low. And when it's high, this will run, which is inside the conditions. The condition will be true. So this is why we're using this if condition. The same applies for the active low push button, but we just added not since the conditions are reversed. We want to detect when it's pressed, and when it's pressed, it becomes low. So we need this to be true when it's low. So we add a not, so this will return low, all of this will return low, and then will be affected by this not, making it 1 or true. So the condition inside will run. This was a quick revision. Here we're using the push buttons to detect input from the user, and then for the LEDs, we're using them as outputs to indicate that the push button is being pressed or any other indication we need. These are just useful for indications in general. And that's it. Let's continue with the timers. So timers, hardware timers are used for timing and counting operations, allowing the processor to carry on with some other process while the timer process runs. Usually, the timer is used with an interrupt. An interrupt is a request for the processor to interrupt the currently executed code so that another event can be processed in a timely manner. So for example, if the code is running inside main, the interrupt stops the main code from executing, runs the code inside the interrupt function, and then goes back inside the main function. So we'll just see in a while. We will not change anything with our Proteus setup. We'll just use the LED, but this time we'll be using the timer interrupt to control the LED. So if we go back to the STM32Cube IDE, let's go back to the IOC file. This time we're going to the timers tab. So this is the timers tab, and we're going to select timer 2. You can notice that some timers have this yellow triangle, warning triangle. This is because we're using the bins for this timer PWM, for example, for another purpose, which is, for example, the inputs or the outputs. So that's why they're showing a little warning. So we don't care. We just use timer 2. So we're presented with a lot of options, out of which we need to choose the clock source. We're using the internal clock or the internal oscillator, so we'll choose the internal clock. We don't need to choose the slave mode or the trigger source, since for the slave mode, it's a mode where another timer controls this timer, or vice versa. We don't need this right now. For the trigger source, we can set the trigger source for the timer to be something else, an external interrupt, an external pin, but we also don't need this. The channels may be used for input capture, output capture, or PWM generation. But for now, we just need this timer and its interrupt, so we'll not choose any channel. Then there are some other settings. We have the prescaler, the counter mode, the period, and the auto reload preload. Also the division, but we're not going to set the division. So we need to set the interrupt to interrupt, let's say, every 200 milliseconds also. So we need to calculate based on the clock we have to get a 200 millisecond interrupt. So the equation for calculating the interrupt is this one. We have the prescaler multiplied by the period over the clock, where the clock is the microcontroller clock we just set at the beginning, configured to be 64 megahertz. If we look back to the clock configuration, these are for the timers for APP2 timer and APP1 timer. These are 64 megahertz. So this is the clock meant And then the prescaler and the period will just now set. So let's go back. Usually, you want to set the prescaler to be the same as the clock, but let's say if the clock is 64 megahertz, so it'll just either 64, 640, or a multiple of this. We'll just get a solid number. And then we can calculate the period using a calculator. If we shift solve for the period, we'll just do the prescaler over the prescaler multiply x over the clock equals, for example, in case we need 200 milliseconds, so it's going to be 0.2 seconds, so equals 0.2. And we're going to solve for the period. So let's type in 640 multiply x over 64 multiply 10 power 6, since it's megahertz, equals 0.2. And then we just solve for x. So the value of x would be 20K. 20. For your information, the maximum value is 65535, and this is because the timer registers are 16-bit registers. So 2 power 16 is 65536, but we're starting from 0, so it's from 0 to 65535. So these are the maximum values for the prescaler and for the counter. So we wanted to count up until it reaches 20K, and then it's gonna restart. So we need to enable the auto reload. This just enables it to restart when it overflows. Next, we need to go to the NVIC settings and enable the interrupt. Timer 2 global interrupt enabled. So far, does anyone have any question?
Can you show the clock configuration again?
Yep. Oh, this one? Clock configuration?
Yeah, this one, clock configuration. Or screenshot it, because...
Okay. I'll send it directly to the group.
All right.
Just to remind, it shows this PLL clock to increase the clock speed for the microcontroller. If we choose only the internal oscillator, it would just be 8 megahertz. But in order to increase the speed, we choose the PLL clock and multiply by 16 to get the 64 clock.
There's a question in the chat. What is the difference between using interrupt and using a delay?
Using a delay might be inaccurate. The SysTick timer is not as accurate as the hardware timer. And the interrupt can be run without stopping the main program. So you don't have to delay the main program. By delaying the main program, you stop the execution of all other tasks. But if you use an interrupt, then your main program can continue working while the interrupt happens. We'll just see now when we get to the code part. The interrupt will be totally separate from the main code and will run separately. So any questions so far? Should I continue?
Just to make sure, that 20,000 we have calculated is the X we have calculated in the equation, right?
Yep. Yep. Let me also send the equation. Okay, so I'll continue. Once everything is done here and the NVIC is set to enable for this one, or just Control S to generate the code. Once the code is done, we can now notice that we have a timer 2 initialization function. So this contains all the settings we just now configured. So we're using timer 2. Rescaler is 640. It's counting up. The period is 20K that we just now calculated. There is no division, and the auto reload preload is enabled. You can see some other configurations, like the clock source is an internal clock source using the internal oscillator. We also configured this one. And for the master slave mode, it's disabled. You can also see that this function halt timer base MSB in it contains the initialization for the clock and for the interrupt also. So this is the clock enabled for timer 2. And then we're enabling the interrupt. Here you can notice that there's set priority. Because there can be multiple interrupts, there has to be an order of priorities in case 2 interrupts occur at the same time. So let's say you have 2 interrupts and they both occur or interrupt at the same time. The timer with the higher priority will run first, and then after it's done, the interrupt with the lower priority will run. But the priority is inversed. So 0 is the highest priority, 1 is the second highest, and so on. And then we just enable the IRQ. IRQ is the interrupt service routine. We're passing the timer to IRQN as the variable to enable. There's also the deinitialize or to stop, which just disables the clock and disables the IRQ. This function is being called inside the halt timer base init function. So if we go to F3, go inside the function. Okay, this is the definition. We go to drivers, and then go to source, then timer.c. You can see all the functions. We go to initialize and scroll down. You can see the MSB init function, this one. So this is being called inside the init. So this function is being called inside this function. So is everything all right so far? We didn't change anything. I'm just explaining the generated code. And then there's one more change. Let's just close these first. Inside the file for the interrupt, which is the IT file, you'll notice that we now have 2 more. We have 1 more. If you go scroll down, you have timer 2 IRQ handler. This is the interrupt itself. The code we write here will happen every 200 milliseconds, according to our calculation, whatever we put here. So if we need to toggle the pin, for example, we'll just add the code here. So hall underscore Gpio, then control space, then toggle pin, toggling pin Gpio P, pin 1. Toggle is the same as right, but it changes every time. If it's set, then it resets. If it's reset, then it sets. every 200 milliseconds, this toggle pin will run. And then this is the IRQ handler. This just clears the flags for the interrupt. So it's no use to actually explain what's inside. But if you are curious, you can check the reference manual and check the registers to be clear, or just check inside this function to see. Let's clear the main function. We don't need this anymore. Let's comment this. So whatever you want to write inside while one, the interrupt will happen separately. So now even if we don't have anything inside while one, the LED will continue blinking at the rate of 200 milliseconds. Let's build Control V. So far, does anyone have any problem regarding the code? We just added this line, and then we commented what's inside the main function. Inside the while, just commented this one. So our while one is now empty, but our interrupt inside the it.c now has the toggle pin. Any questions so far? If no, then I'll just go to the simulation. Again, the hex file is already loaded, so we don't need to load it again. And then we need to do one more thing. By default, the timer doesn't begin or doesn't start, so we need to start the timer. So inside the user code begin, we can add all underscore timer, then press Control space. Then we need the base timer, which is this base start. There are 3 base starts. One is just base start without the interrupt. One is base start DMA, which is direct memory access, out of scope for our workshop, but if you're curious, you can check the reference manual. We're going to be using the base start IT, which is the interrupt. Then we're also going to pass the same time 2. This is the same one used inside the initialization here. One. And we're adding the address to pass by reference. This address is necessary since the function itself needs a pointer. So that's it. So now, once it starts and the interrupt starts, the LED will keep blinking. We'll just build again. If we go back, press run, the LED should blink every 200 milliseconds. So again, our main code is now empty. Just the interrupt is in control of this LED. So this is why the interrupt is useful. We can do something repeatedly without interrupting the main program. So this LED, for example, can be used to indicate that the microcontroller didn't hang or nothing bad happened while the main code is running. This is always blinking, for example. So any questions regarding the interrupt and the time? Any questions regarding the calculation for the clock or the period? If no, then continue. Okay. So let's say we want to change the speed at which the LED is blinking. So we need to change the period or the prescaler. So let's add back the F condition, but this time, instead of setting or resetting the LED, let's change the period of the timer. So if we need to change the period, we need to change the register that has the period. Or alternatively, we can de-initialize the timer and then initialize back with different settings. But this is too much work. So instead, we'll just edit the register that has the period. So if you go to the reference manual, this is the reference manual. You can see there are different types of timers. From one and timer 1 and timer 8 are advanced control timers. But with our board or with our microcontroller, we only have 1, 2, and 3. So timer 1 is an advanced control timer. And then we have general purpose timers, which is timer 2 to timer 5. So timer 2 and 3 are general purpose timers. The difference between the advanced control timers and the general purpose timers are just the amount of supported uses. So if we read for the general purpose timers, we can see that it's measuring pulse length of input signals or generating output waveforms, which is output compare and PWM. But for the advanced control timers, we have much more. We have including also measuring the pulse length of input signals and generating waveforms, output compare and PWM. But they also have complementary PWM, which is just PWM flipped for the other channels with the time insertion. So they're just the same basic timers, but with different features and have additional features. So we can use both of them. We're using timer 2, so we can go to general purpose timers and scroll down to registers for the reference manual. Once we click on timer registers, we can see the different registers, but we're only concerned with the prescaler and the period, so we can just scroll down until we can see the prescaler and the period. This is input capture mode. This is the output compare, and so on. This is the timer count itself. This has the timer count currently from, let's say, we set the period to 20K. So if you read this at any point, it would be any value between 0 and 20K, depending on the count. This is the prescaler, which we want, which is PSC. And then there is also the ARR, stands for auto reload register, which is also used for the period. So this is the period register. You can read the definition here. ARR is the value to be loaded in the actual auto reload register. There is also this prescaler. The counter clock frequency, counter, is equal to the frequency divided by the prescaler. For now, let's just change the auto reload register, which is the period value. So let's say if I click the first push button, we'll access the timer, which is timer 2 dot instance. So if you just press dot, you have a lot of options. These are the initialization options and some other options. But instance is the timer register itself. So we'll click on instance. And then inside, we'll choose the ARR register. With this register chosen, we can just equal something. So let's set this to 20K. This is the default. If I press this one, it's 20K. If I press the other push button, let's bring it down to 5K maybe. So 5K is going to be a 50 millisecond interrupt. You can recalculate to figure out exactly how much, but it's going to be 50K, I think. 50 millisecond. So that's it. Now we can change the value or how fast the timer interrupts while pressing the push buttons. So if you build this one, go back and simulate. So currently it should be the default 20K. So it should light up and light off. This will also make it 20K. So let's press this one, which is the 5K. So when this one is pressed, now it should be faster. It should interrupt at a faster rate. Wait for a while. Wait, hang. Oh, okay. So now it's blinking at a faster rate. If you want to go back to 20K, then just press this one again. So now it's back to interrupting at 200 milliseconds. So any questions so far?
Can you repeat the coding part again? Especially how did you make the second push button with a 20K time? Again, please.
And this part?
Yes, exactly this part.
Yeah, okay. So this is the same for reading the push button. So this is for reading the push button connected to A11, which is this push button 1 is connected to A11. So this is an active high push button. So it will be 0, which is connected to this one until this switch is closed. So connect 5. So we're just reading. By default, when we read this, it will be 0. So this will be false if 0 is false. When it gets 1, it'll be F1, so it will go inside. So this part, this is the timer 2 initialization struct, which was used or was already defined on the auto-generated code here. And we used to initialize the timer. As you can see, the timer instance is set to timer 2. So this is the timer 2 register itself, or the timer 2 collection of registers. Then, inside main, we also access this instance, and then access the ARR register. So the ARR register is the register for auto reload, which is the period register. If we go back to the IOC, you can see that next to the period, there is auto reload register. If we expand this a bit, auto reload register, 16 bits value. So the counter period is actually the auto reload register. So we just access this ARR. You can see that this has an arrow, which is different from this dot. This is because the instance itself is a pointer. So when a struct is a pointer, the children of the struct are pointed to with this arrow instead of the usual dot. So this is just the child of instance. Instance has a child called ARR. If you go to instance, go to timer time, fine, and see the registers inside. Loads. Yeah, so these are all the children of the timer type defined, which instance is a pointer to. So what we did, we referred to the ARR register inside the timer 2 instance and set it to 20K, which is the initial period value. We set also inside the initialization. For the second push button, it's active low, so we added a NOT. So usually it reads 5 volts, or will be read as 1 for digital. So if f of not 1 is f of 0, so it's false. And if it is pressed, so it will result in low, which is 0. So not 0 is 1, so f of 1 is true. So this will run. We're doing the same, just accessing the ARR register and setting it to 5K instead. So we're just changing the period for the interrupt. What you can do is, or you can also de-initialize the timer reinitialize again with the new value, but this takes so much space in the code, so it's not efficient. You can reinitialize this one by change the period, but this takes so much space. So, any other questions? If no, then this is the end for the second session, which is the timer session. The next session will be discussing the Uart interface. So do you want to give like time for Q&A or a break, or? Or should we just continue to the Uart session? Okay, let's continue then. So the Uart interface, or Universal Asynchronous Receiver Transmitter, is one of the most used device-to-device communication protocols. So Uart is used for communication between devices. It's also a serial communication protocol, so it means that data is transferred bit by bit. And it's two-way, meaning that it uses two wires, one TX and one RX, to send data or receive data. So this is the typical connection for Uart. We have two devices, each with a TX and RX. The TX of one device is connected to the RX of the other device. So it transmits data to the other one's receiver end, and so on. So this is the Uart connection. Let's go back to Proteus and add something so that we can receive the Uart messages sent by the microcontroller. Go to this one, which is the Instruments tab. And then we're going to select the virtual terminal. We're just adding one virtual terminal. Just add, and then right-click and mirror so that we can directly connect. So let's check the data sheet to find the TX and RX for the Uart interface for our microcontroller. So if you go to the data sheet, not the reference manual, the data sheet this time, and then go to the pinouts and pin description, you can scroll down until we find a table containing each of the pins and what they can be used for. So this one, which is A2, can be used as UART2's TX, and A3 can be used as UART2's RX. It can also be used for ADC or the timer channels, but we're just going to use it for UART for now. So let's connect. A2 was the TX, so we're connecting to an RX, to the RX. RX is A2. And TX is connecting to the RX, which is A3. So far, does anyone have a question? Okay, so let's continue. Now that we've wired the virtual terminal, let's go back to the STM32Cube IDE, to the IOC, and let's enable the Uart. So under connectivity, we can find the communication protocols. We're going to choose the UART2. And then there are multiple choices for the mode. There's asynchronous, which we're going to use. And there is the synchronous, which requires an extra line for clock synchronizing. So there's a clock between two devices. When a device sends, it also updates the clock and so on. There's single wire, which is half duplex. So one single wire is used for either TX or RX. And there are so much more modes, but we're just gonna use the asynchronous type for now. There's also hardware flow control, which we'll leave as disabled. This is used when one device is faster or one device is slower than the other device. So hardware flow control can be used to synchronize both devices if the baud rate is different. Baud rate is just the rate of sending data. You might have already seen the classic 9600 baud rate, used usually for the Arduino serial. When you usually serial.begin and then type in 9600, which is the baud rate. And then the word length is the length of the data we're sending. The parity bit is either set to none, which is no parity, odd or even. An odd parity means that the number of ones inside the data sent must be odd. So if it's even, then the parity bit will be set to 1 to make the total number of ones to odd, and so on for the even also, even parity. For now, let's just leave it as none. The stop bits indicate that data is already sent. This is stop, so you just leave it at 1 bit. So that's all for the UART. You can see that A2 is already configured as the TX, and A3 is configured as the RX, just by enabling the asynchronous mode. You can then go ahead and control save, control S, and then say yes to generating the code, and the code should start generating. Okay, the code should remain the same, except now we have Uart initialization. So if you go to this one, press F3 to go to the function, and let's see. These are the same settings we just configured. This is the baud rate, 9600. The word length is 8 bits. The stop bit is 1 bit. The parity is none. It's TX and RX. There's no hardware control. The speed will be the same. Then oversampling. Oversampling is when receiving, 1 bit will be sampled 16 times, whether it's 0 or 1, just to make sure that there's no error in receiving. But since we'll be sending from this microcontroller, so we're not really concerned about the oversampling. And then Uart initialize to just initialize the struct that we just loaded, which is also defined here. And same, it's using a pointer, so we're passing an address. So if we go back to our main code, we can start using the Uart to send data to the virtual terminal. So first, let's add something. Let's say counter and counter equals 0. Then let's increase this counter when we press this button, or decrease it when we press this button. So let's just increase counter plus, then counter times. We also need to prevent the button from being pressed multiple times. So we can add a while loop here, just to make sure that the button is pressed once. So if we press the button, it goes inside the if loop. Then while it's still pressed, while this is still true, we're just gonna stay in this area until it's no longer true. So the push button is no longer active, and it can continue to the next one. So this ensures that when we press the push button, it only registers at 1 press. And do the same for the second one. Also add the not and change this one to 12. And that's active low. So now we have a counter that increases or decreases. The next step is to load this into something, into data, and then send it with UART. Let's create a character array called data, for example. Let's set it to 100. The array length is 100. We need then to load the value of counter into data. For this, we'll use a function called sprintf. But we need to first add that include stdio.h. We just added this one, so we can use the sprintf function. So after increasing the counter, let's sprintf. The first argument for sprintf is the data itself that we're going to load into, so data. Then the format. Format follows the printf format, so we can just try counter, then %d for an end, then comma, and load in the counter. Now the value of data is going to be counter, and then the value of this counter variable. Let's do the same for the second if condition. Then let's actually send data with UART. So it's going to be the same haul, and then underscore UART, and then control and space to show the available functions. Then we're going to scroll until we find transmit. So there's also 3 types of transmitting. Just the normal transmit, which we're going to use. There's DMA transmitting, direct memory access. You can read more on it inside the reference manual. And there's the interrupt transmission, means begin the sending and then interrupt when it finishes sending. But we're just going to use the normal transmission. So we're going to pass the UART struct that was already initialized, which is UART2. And then the data is data. Then size. Size is the size of data. So we're going to use the function called sizeOf. Then pass in data. This way we have the size of data without actually needing to calculate how many bits are inside data. And then we have timeout. Timeout is the time until it no longer attempts to send. So if your data is too long or something, then the timeout will cut it off. So let's set the timeout as like 50 or something. 50 milliseconds is a lot of time for data to be sent, since the microprocessor is at a 64 megahertz speed. So this should be enough. Let's do the same for the second push button. Let's copy this here. And then let's add just one more thing for utility. We want this to go to the next line every time. So normally with printf, we just use \n, but here we need to add also \r. So \r/n. \r is just carriage return. So it returns cursor to the beginning and then next line. So this is the same here. Then we're done. So what's going to happen basically is when you press the push button, the counter increases, and then the UART is going to send to the virtual terminal counter and then the value of counter after increasing or after decreasing, depending on the push button pressed. Keep in mind that the interrupt is still on, so the LED will still keep on toggling while all of this is happening. So this is why interrupt is useful. Okay, let's press on Control P to generate the hex file. Any questions so far?
I have a question regarding the when we went to usart.c.
Yep, let me go.
I saw you like expand something. I expand this
Which
the
one?
void mx usart2
Yeah.
void. I think it's line 31 on yours. Yeah. How
Yeah.
did you expand it?
Expand.
And yeah, expand.
Oh, it's not expand. I was inside main.c and then I pressed on F3. Press on F3, then it went to usr.c where the function is. It's already expanded. You can retract it if you press this one. This mini minus button beside the function.
All right.
So, any more questions regarding the code? You can see there's a warning. There are 2 warnings. So this because your transmit expects an unsigned end. So what we can do is cast this data. An unsigned end is also 8 bits, the same size as character. But we can just, if we ignore the warning, it will still work. So we can just cast it to remove the warning. Let's run T. T. So this cast data. So data is now an unsigned end of 8 bits and should remove the warning. They're at the same side, carry the same data, so it shouldn't matter. Test this one. Then Control B again, the warnings should be removed. So any other questions regarding the code? Don't forget to include the stdio.h to use the sprintf function. Okay. So let's continue. Just go back to this one and let's double click to make sure that the baud rate is set also to 9600. The same settings, 8 bits, no parity, and 1 stop bit. They're already by default the same settings, so just press OK. Now we're ready to simulate. Let's press A. You can see a small virtual terminal open. The LED is still blinking. And if we press this push button, it should increase counter by 1 and print also. So counter 1. If we press this one, it should decrease back to 0 and printed at the virtual terminal. So can keep on increasing and it will keep on printing. Same should we should also decrease and it will keep decreasing. Even if we go below 0, it will just be -1. So any question regarding this entire section, which is the Uart section?
I have a question, but it's in C,
Oh,
C language. Why did we use a sprint, especially a sprintf?
We're using sprintf to load this inside the data. Otherwise, if we want to load this or any other string inside data, we'll have to use a for function to load every single character inside, which is very tedious. So sprintf is much easier to use. It's the same as printf, but instead of printing to the terminal, it prints inside the data argument, which is the first argument. Then we can later transmit. So this is why we're using sprintf. We're also using sizeof here to avoid calculating the size of data, or since the sizeof is already calculating the size of data. So just use the size of data. Any other question regarding the UART section? Okay, if no, then this is the end of the UART session. You wanna take Q&As or take a break? Or is it okay if I continue? Okay, let's continue. Oh, need to go play Mac. We'll just finish shortly.
Yeah. So Peter, we take a small
Okay.
break for praying first.
Okay.
So I think Maghrib will be from 7:20. So we can take 10 minutes break for now.
Okay.
To present the task and the example. So we are going to continue. I'm passing to Anas.
Yep. Hello. So finally, we're giving you guys a task. So this is day one task. You need to design a system that can calculate the speed for runner in a certain area. These are the task requirements. The speed needs to be displayed after the runner passes. And then you can choose your own sensors or hardware. You need to simulate the system using Proteus, just like what we did just now. You can use whatever peripheral you want to complete the task. You are not limited to the peripherals that we discussed today. Submit then the proposal along with Proteus project and the code. The proposal, I mean, for the sensors and for the hardware for the entire system that you design. It can be either a docs file, PDF file, a PowerPoint presentation, or even a link to a YouTube video if you want to explain. It's up to you. One way you can complete this task is, for example, set 2 sensors. Once he passes by the first sensor, you start the counting using the timer interrupt. And then when he passes the second sensor, you stop the timer and calculate the time between passing of the 2 sensors. And then since the distance between the sensors is known already, you can calculate the speed, distance over the time that you got from the timer, and the interrupt timer. And then just display it using Uart, send it to a virtual terminal, and display. You can do it this way, or you can do it another way using different sensors, using different peripherals. It's up to you. But we'll give a certificate, a special certificate, to the best submission for the task. So you're encouraged to be as creative as you can. So that's all for the task explanation. Anything else you want to ask about for the task? Any details about the task?
We can tomorrow do the task before we start our day 2 materials. We can do the task and show the participants maybe one solution we can do, right?
Okay. Okay. Any other question? Which type of sensor that we need to use? Any sensor, you choose your own sensor and include it inside the proposal, and then we'll decide if it's a nice sensor or no. You just need to find a way to calculate the speed of a passing runner. You want to put 2 sensors, calculate the time in between. You want to use another method, it's up to you. As long as the solution contains a microcontroller and uses the peripherals, either the ones we learned, or you can use other peripherals. You can use external interrupt, whatever you want to use. Any other questions?
Right, I think there's no more questions now. So we can close day 1 progress. Okay, we have reached the end of day 1. We hope that you have followed us throughout this day 1 program. We still have more materials to finish tomorrow, as well as we need to finalize our project tomorrow. So we can't wait to see you again tomorrow. Thank you for attending today. Have a nice day and good night all. For the attendance form, we have sent the attendance form previously. I'm going to share it again.